Hello everyone, this is part 2 of J.J. Thompson's charge to mass experiment. Last time we left off with starting the solution, but remember, here's the first page notes. There's a link that you should watch to how to set up the experiment. These are the equations you're going to solve. I'm going to solve these equations by letting everything equal 1 in the steps to the solution. So these are the two general equations. You could label this guy as number 1, and this one is number 2. And then also note the initial conditions. And we're going to prove that these equations with the initial conditions lead us to the path of a cycloid, like we talked about. So we're going to start with the two equations, as we had left off in the last video. And note the first one's non-homogeneous, second one's homogeneous. Here's the initial conditions. The idea of solving this system is really just to solve by substitution. They both involve x and two different functions, x and y, and their derivatives. So what we could do is, let's say, take this first equation, solve for y prime, calculate y double prime, substitute it into this equation, and then it'll be an equation in terms of x and its derivatives. And then we'll do the reverse of that, and we'll come up with the solution for y. So the first time we're going to get this in terms of x, we'll be able to find the solution for x. Second time we're going to get this equation in terms of y by solving this one for x prime, calculating x double prime, and substituting. Then this will be in terms of y, and we'll be able to solve that equation for y. And then there's going to be more. But let's start by taking number 1. X double prime plus y prime is 1. And we're going to solve that for y prime. So just say y prime is x double prime minus 1. And then calculate y double prime. And y double prime would be x triple prime. Okay, now we're going to substitute that into number 2. So equation 2 was y double prime minus x prime is 0. So y double prime is x triple prime. So x triple prime minus x prime is 0. And actually made a little mistake here. There should be a negative x double prime, right? Because I transposed the x double prime. So that would leave this as a negative x triple prime. So then this would be minus x triple prime minus x prime is 0. Excuse me. Okay, so notice that that is a homogeneous equation. And so we can get the characteristic equation. So minus r cubed, minus r is going to be 0. So again, that's minus r cubed. Let's multiply it by negative 1. So r cubed plus r is 0. Factor in r. Set them to 0. R is 0. R squared plus 1 is 0. So r squared is negative 1, and r is plus or minus I. Okay, so from that, those roots, we come up with an equation for x, which would be, okay, I'll show it explicitly. C1 e to the 0. Now the independent variable is t here. So C1 e to the 0t. And then plus, so that takes care of the root of r equaling 0. Complex conjugate pairs, e to the ax. A is 0. So e to the 0t. And then times, I left off with C1. So C2 cosine of bt. B is 1. So 1t, or just simply t. And then plus C3 sine of t. Okay, so that gives us a solution for x But we're going to have to solve for these constants at some point. But C1 plus C2 cosine t plus C3 sine of t. And we're going to need to come back to this, so I'm going to box it off, and I'm going to label it as Roman numeral, or Arabic numeral 1. Okay, so now we're going to do the same thing, but in reverse. That is, we're going to take equation number 2, which was y double prime minus x prime is 0. We're going to solve this now for x prime, calculate x double prime, and then substitute it into the first. So here we get x prime is y double prime. So then x double prime is y triple prime, and substituting into equation 1, or rewrite the equation again, it was x double prime plus y prime is 1. So x double prime was y triple prime plus y prime is 1. So y triple prime was from right there. Okay, notice that this is non-homogeneous. Okay, and if it's non-homogeneous, then recall that the solution, okay, it is for y, is going to be in two parts. The complementary function plus the particular solution, where the complementary is the solution to the homogeneous, and the particular the solution to the non-homogeneous. So first off, we form the associated homogeneous equation. So that's y triple prime plus y prime is 0, because it's homogeneous, of course, setting it equal to 0. And now we can get the characteristic equation. So r cubed plus r is 0. Similar to the last solution, factor out an r. R squared plus 1 is 0. So r is 0 and r squared plus 1 is 0. Giving us r squared is negative 1. And r is plus or minus I again. So then we can get from these roots the general solution for y sub c. And that would be, now since we left off with C3 up here, let's start with C4. So C4, I'll be explicit again, e to the 0t, and that's coming from the r equaling 0 root. And then plus complex conjugate pairs again, e to the at, a is 0, so e to the 0t, and then times, looks like C5, cosine bt, b is 1 again, so cosine t, plus C6 sine of t. And so let's simplify that. And we y sub c is C4 plus C5 cosine t plus C6 sine of t. Okay, and I'm going to box that off for now. Actually, you know what? I'm not going to box it off, and the reason why I'm not going to box it off is because that's not the general solution for y. That's only the solution to the complementary, to the homogeneous differential equation. So now we have to find the particular solution. Because remember, this equation here was non-homogeneous. So there's the complementary y sub c. Now we need y sub p. So let's say now we need y sub p. So this is by the method of undetermined coefficients. Remember, we make a guess for y sub p based on the function that the differential equation is equal to. It's causing it to be non-homogeneous. Well, it's just a constant term. It's just some number. So we call it A. But then when we make our comparison, we see that there's a duplication. So there is a dupe. And that is because C4 is just a constant. So therefore, we have to multiply by the least power of t. That's going to cause it not to be a duplication, and that would just simply be t to the first. So then we could take our y sub p to be a times t. Okay, so then at that point, to solve for a, we're going to have to calculate some derivatives. Y sub p prime is a, y sub p double prime would be 0, and y sub p triple prime would be 0 as well. And we're going to take these and substitute into the different non-homogeneous differential equation up here. It was y triple prime plus y prime is 1. So therefore 0 is y triple prime plus a is y prime must be 1. So a is 1. So then that means that y sub p is going to be 1t, or just simply t, because y sub p after multiplying by the t was a t. So 1t or t. Okay, so now we could say that y is y sub c plus y sub p, and that would be y sub c, that's up here, c4 plus c5 cosine t plus c6 sine of t, and then plus y sub p, which was just simply t. And that's the equation that I want to box off. So those are the two main solutions. But one thing to, and I'll call that Arabic numeral 2. But one thing to notice about those two solutions is if you look at the constants, there's actually 6 constants, C1 through C6. And remember, we needed as many initial conditions as we have constants in order to be able to solve. If you look at the initial conditions, there were only 4 of them. So let me just mention this before I go to the next page. Let me say now we need to solve for the constants. But there are only and there's 6 of them. But there are only 4 initial conditions. Okay, so we're going to have to do something a little bit fancy to be able to determine those constants. So I got a second page here that's just a blank sheet, and we'll consider, let's say, the equation that we called Roman numeral 2. Okay, now, so this is from the first page. That equation was y double prime minus x prime is 0. And so I wanted to choose that equation to start to work with because it's homogeneous. And it's simpler than this, obviously, the non-homogeneous. I mean, not dramatically simpler, but it is. But consider that equation where we've already established, where we know that x equaling, okay, what we found, this was equation 1, x was, so now I'm back here, C1 plus C2 cosine t plus C3 sin t. And also consider that y, we had a solution for that. Okay, that's right there. C4 plus C5 cosine t plus C6 sine of t plus t. Okay, so we know those two equations satisfy this differential equation. So let's substitute. We'll calculate x prime first. We get minus C2 times the sine of t plus C3 cosine t. Okay, so that's x prime. Here we'll need to calculate two derivatives because we've got y double prime. So y sub prime is minus C5 sine of t. Derivative C4 and C1 are both 0 because those are constants. And then plus C6 cosine t, but then plus 1, so don't forget the derivative of t. But then we need y double prime as well, so that's minus C5 cosine t minus C6 sine of t, and then the derivative of 1 is 0. So at that point, we're going to substitute into the equation Roman numeral 2. Oh, and this was the equation Arabic Roman numeral 2. But now we're going to substitute those into Roman numeral 2, the y double prime minus x prime equaling 0. So y double prime minus C5 cosine t minus C6 sine of t minus x prime, I'll use parentheses here, minus C2 sine of t plus C3 cosine t, and that has to equal 0. So now we'll compare. Let's compare first off sines of t. If I compare the sine of t's, I've got minus C6 sine t plus C2 sine t equaling 0 sine t, because there's no sines on the right. Dividing out the sine t's, minus C6 plus C2 would be 0, so therefore C2 is equal to C6. So that's something we know. Now, we'll compare cosine t, and on the left we've got minus C5 cosine t. Distributing this negative would make it minus C3 cosine t equaling 0 cosine t. Excuse me. Dividing out those cosines, minus C5 minus C3 is 0, and I'm going to say that C3 is negative C5. Okay, so we'll have to hold on to those for now. And now we'll consider the two solutions where number 1 was x equals C1 plus C2 cosine t plus C3 sine of t, and number 2 was y equals C4 plus C5 cosine t plus C6 sine of t plus t. And these equations now become x equaling, okay, C1, but C2 is C6, so plus C6 cosine t, and C3 is negative C5, so minus C5 sine of t. And I'll just recopy this one because we're going to keep those constants the same. Okay, and we're getting close now, because now what we could do, those are the solutions. Notice there's only 4 different constants, C1, C4, C5, and C6. So now we could use the initial conditions and solve for those constants, and we'll be able to substitute them in, and then we'll be done. So the initial conditions are going to require us to calculate the derivatives of x and y respectively. So x prime is negative C6 sine of t minus C5 cosine t, and y prime is negative C5 sine of t plus C6 cosine of t plus 1. Don't forget derivative of t is 1. And now the initial conditions. Okay, remember, the initial conditions were x was 0, y was 0, x prime was 0, y prime was 0. So from x equaling 0, we get 0. So we're up here. 0 is equal to C1. And remember, when t is 0, cosine of 0 is 1, sine of 0 is 0. So C1 plus C2. And so, or C1 plus C6, excuse me. Hold on one second. Okay, I'm good. Sorry, I'm looking here. We're looking at this equation. I had looked at that one, so it's not C1 plus C2, it's C1 plus C6. So we're going to have to hold on to that. Put little brackets around it. Okay, and then let's see, what other ones do we have? We have that x. Let me do a y. Let me do the y's over here. Y is 0 gives us. Okay, so then I'm in this equation. 0 equals C4 plus C5. And we're going to have to hold on to that one too. But then x prime of 0 is 0. Gives us that 0 equals, okay, now we're here, x prime. Getting sine of 0 is 0, cosine of 0 is 1. So negative C5. So that means C5 is 0. Alright, so that's one of them. Y prime of 0 is 0. Gives us, so now we're here, y prime, 0 equals, again, sine of 0 is 0, cosine of 0 is 1, so C6 plus 1, so C6 is negative 1. Okay, so now we'll work our way back to these brackets. I guess I'll just say back substitute. We had C0 is C1 plus C6, but C6 was negative 1, so 0 equals C1 minus 1, so C1 is 1. Where else can we go? I guess we can go up here to the other bracketed equation. 0 equals C4 plus C5, but C5 is 0, so C4 is 0. Okay, and then we have C2 is C6. We already had C6, so C2 was C6. So C2 is -1, so these are these circled equations up here I'm going to. And then we also had that C3 was negative C5, but C5 was 0, so C3 must be 0. And I think we have them all. Just to summarize, C1 is 1, C2 -1, C3 0, C4 0, C5 was 0, and C6 was -1. And so now finally we have the equations were, okay, back up here, x was C1 plus C6 cosine t minus C5 sine of t. This becomes C1 was 1, C6 -1, so 1 minus cosine t, and that's what we were looking for. And then similarly y, which was, because C5 was 0, sorry, and what it was C4 plus C5 cosine t plus C6 sine of t plus 1, and so substituting C4 is 0, C5 is 0, C6 was a, I recopied this, it was a -1. I recopied it wrong right here, I had it right there, of course. So C6 was a -1, so -1 sine t, or just negative sine t plus 1. And that's the other equation we were trying to prove. Or plus t, I'm sorry. So that was a plus t, and this is plus t as well. And that was the other equation that we were trying to prove. Okay, so that's it. We just made it under 30 minutes. Next part's going to be very important. I'm going to show you how to at least start the problem in terms of, you know, the mass m, h, the magnetic field intensity, E, the electric charge, and E, the electric field. So I'm going to show you how to start your first problem on your next exam, and we'll see you next time.